All right, so now we're going to talk about first order kinetics, and if you didn't catch it, that was the reason. That's the tie-in for the Star Wars theme song, first order. All right, so let's consider this hypothetical reaction. A decomposing into 2B plus 2C. We have studied this hypothetical reaction before, and we defined rates, and we said that we could, if we were so inclined, say that the rate of change, the rate of this reaction, is equal to the change in concentration of A divided by the change in time, and that is equal to this product of K times A. So this is the rate. And to review our vocabulary here, let's not forget that this is the rate law. Now remember, there's exponents here, and if you don't see it, it's understood to be 1. And because that exponent is 1, this is said to be first order with respect to A. If that exponent would have been 2, second order, exponent is 3, third order, so on and so forth. Now, because there is only one component in that rate law, this reaction is also said to be first order overall. Now, the overall order is just the sum of all the individual orders. So if, for example, you have something that's first order with respect to, component A and first order with respect to component M, then it's second order overall. And it is important to know that first order overall, which by definition as first order with respect to a single component, is by far the simplest case. And now, so the rate law, remember, was useful, sort of, and I use the term loosely here, because it would tell you if you plugged in this concentration and the rate law, the rate constant K, it would tell you what the rate of the reaction was at that particular set of concentrations. But a more useful thing would be an expression that tells you what's the concentration going to be after a certain amount of time has passed. If I have initial concentration of 1 mole per liter, what's it going to be an hour later? What's it going to be a day later? Or work backwards. And if I measure the concentration of a drug in someone at a certain time, what was it an hour ago? And this is a little more complicated than you might think. Now remember that the rate constants were, as the name implies, constant. But the rate, the actual rate, is ever changing because the rates also depend on the instantaneous concentrations. So figuring out the concentration after an hour has passed is a little more complicated than you might initially think because the rate is not constant throughout that hour. It's continually slowing down as the concentration of A goes down. And it turns out that you need calculus to actually do this. Now, once you've got the calculus, it's actually quite trivial. But for this class, I just give you the answer. And here it is. All right, so let me show you right now everything means here. So this is just a concentration of A at time t. That is the initial concentration of A at time 0, is what we call that. That t is the elapsed time. K here is the rate constant from yesterday. And last but not least, this E is just the base of the natural log system, so it is just a number that is equal to 2.71 and a bunch more digits. That's pretty much it. All right. Now, you might see this in another way. You not might, you probably will. If you get rid of that e, the base e, this expression, you might see it this way: the natural log of the concentration of A at time t is equal to the natural log of the concentration of A at time 0 minus kt. And the reason why people like this particular version of it is because that's actually a linear equation, and it's easy to graph, it's easy to analyze. But these two are saying exactly the same thing. And in my opinion, this is actually the easier one to use if you're actually looking for concentrations or associated times. All right, and just to show you it's a linear equation, so you've got here y, and then the intercept is going to be the natural log of A at time 0. The slope is the opposite of the rate constant. That's usually how you determine the rate constant. And then the independent variable is just going to be time, usually. All right, so let's work with this. So here's an example. So CP, this is an abbreviation for cyclopropane. What is cyclopropane? It is not a particularly happy camper. It is a molecule that is a 3-membered ring of carbons, and each carbon has 2 hydrogens attached to it. So it's not really a circle, but triangulopropane just doesn't have quite the same ring to it. All right. And so I'm just going to, for obvious reasons, just going to abbreviate that as CP. And let's say that we start out with 0.25 molar of this stuff. And we might ask ourselves, what's the concentration going to be after 8 minutes? And what you need to know is that the rate constant for this reaction is 6.7 times 10 to the negative 4 per second. So that's seconds to the negative 1 at 500 degrees C. Now, remember yesterday, or whenever you listen to those videos, the rate constants are temperature dependent. So reactions usually go faster as you heat it up. And that's why temperatures are usually stated when given a rate constant. So at 600 degrees C, the rate constant would be different. And this is pretty straightforward application of this one. That you are given an initial concentration, you've got the rate constant, and you've got the time. That's the 8.8 minutes. And the only thing you don't have is what the concentration is at the later time. One thing you do need to do, though, is rectify the units. So arguments of E operations, just like natural logs, should technically be unitless. They should just be numbers. Now, in this case, the rate constant K has units of inverse time, and time has units of time, so they would cancel out. But because this is expressed in minutes and this is expressed in seconds, that is not going to happen. So we need to convert the rate constant to inverse minutes, or that time to seconds, and usually it's easier to do the latter. Convert the time to whatever the complementary unit of the rate constant is. So in this case, I'm just going to convert that time to seconds. I've got 8.8 minutes. Hopefully at this point in your lives, you know that there's 60 seconds in every minute, giving us a elapsed time of 528 seconds. And from there on in, it really is just plug and chug. Now, if you were like any of my other 1120 classes, you haven't done this very often in a calculator, so make sure you follow along and can get my answer. And the way I would recommend doing this is that in this order. So using your calculator, what you want to do, and unfortunately, the way that different calculators process E arguments is all a little bit different. But what I would say first is evaluate this product. The 6.7 times 10 to the negative 4 per inverse seconds times 528 seconds, and also change the sign. So it should be a negative quantity altogether. And that should all work out to be about, my pen back here, negative 0.354, and it ends up being unitless. And then you would raise e to the negative 3.54 power. So then do this much. And then when you're all done, you're going to get some number. That ends up being so at this point you will have (0.25) and then .702, and that will give you about 0.18 molar. So make sure that you practice or figure out on your calculator how to do these E operations, because they're a little bit different on each one. Very often you evaluate this expression at like negative 0.354. You'll hit an e to the x button and it'll spit out the 0.702 and then multiply it by the 0.25. But make sure whatever you do, you know what the key punch sequence is to get these answers. The 0.354, and then e to negative 0.354 is 0.702, and then multiply it by the 0.25. Now, does this answer make sense? The question you should always ask yourself, and the answer is yes, because you would expect a lower concentration as time goes by, and 0.18 molar is in fact lower than 0.25 molar. And that's pretty much these problems. So in any one of these expressions, there are four things that go into this expression. The concentration at time t, the initial concentration, the rate constant, and the time. And given any three of those, you should be able to figure out the four. So let's do a different example. Same concept, but it's asking you for a different quantity. Namely, and these are the tricky ones, so they're asking you how long is it going to take to go from 0.25 molar to 0.15 molar. So we're asking you in this case where you've got, you know what the concentration at time t is, you know what the concentration at time 0 is, you know the rate constant. What you don't know is the time. So I'm going to walk you through this one step by step, because that is probably the most complicated form of this equation, of these problems. And know that if you didn't, that this e to the this e is undone by a natural log. So if you have an expression e to the x, if you take the natural log of e to the x, you will get x, and that will come into play shortly. So let's set this up. So this is the setup, and let me just kind of tell you what's what here. Obviously, this is our target concentration, the 0.15 molar, and this is the initial concentration, the 0.25 molar. And we're solving for, now we know the rate constant, so let's not put the number in there, just leave it as a letter, and we're solving for t here. So generally when you're getting ready to undo an E operation, it's best to leave the E expression on one side of the equation and everything else on the other. So I want to divide both sides by 0.25 and get this. So 0.15 divided by 0.25 is equal to e to the negative kt. And you can, now I would evaluate the 0.15 divided by the 0.25, telling me that 0.6 is equal to e to the negative k times t. And here's where you get rid of that e. So what you do here in cases like this is simply take the natural log of both sides, which gives us the natural log of 0.6 is equal to negative k times t. And from here on in, it's kind of the algebra that you are already familiar with. If I want to isolate for the time, which that was our goal here, I would just divide both sides by negative k. And again, don't forget the negative sign, which I have put right here. So the time it took for this reaction is going to be equal to the natural log of 0.6, which is just a number divided by 6.7 times 10 to the negative 4 inverse seconds. And note that inverse seconds in the denominator means seconds. And that means that it's going to take 762 seconds to go from 0.25 molar to 0.15 molar. Does this answer make sense? Well, it should. This is a greater, it does. And if you compare this to the previous problem we went from 0.25 to 0.18 molar, and that took 528 seconds. So this is going for longer, which means that the final concentration should be, this is a greater concentration drop. We're going to 0.15, telling you that this should be a time longer than 528 seconds, and in fact it is. So this answer makes sense. All right. And this is roughly this is the toughest problem that I could probably ask you on an exam. So if you can get through this one, you're fine. And I've got a few more examples.